Yeah, I see it.
Hello, good morning everyone. I'm Malav Patel and with me is my teammate Ganesh Pinnu. Today we are presenting our project Clustering Earthquake Patterns by using density peak clustering, or you can say DPC. Our goal is very clear. Our goal is to explore how we can better analyze seismic data using a method that both accurate and fast, and especially it when it falls with the traditional algorithms. Let's start with why we choose this topic. Earthquakes usually occur in patterns. They form along curved, multi-scale fault lines. But traditional clustering algorithms like k-means, assume, and cluster are curricular or evenly spaced, which is not which is which is not true for real earthquake data. Like DBScan is more flexible, but you need to manually set the distance threshold called ellipse, and that doesn't work well everywhere because you have to set the longitude, latitude on manually. While density peak clustering or the DPC is a different. It can automatically find the number of cluster and adjust to different densities. But the original DPC algorithm is too slow for modern datasets. So we use the optimized version called DPCfast that fixes this problem. Now let's break out how the DPC algorithm works. The first concept is density, which is represented by rho. This count how many nearby points in our cases earthquake earthquake fall within a small fixed radius. Next is the delta, which tells us how far point is from its nearest neighbor that has a higher density. Now we will see that point that have a high rho and high delta are chosen as a cluster center. All other points are assigned by following nearest denser neighbor. Now this process repeats until every point is a part of cluster. And what makes a DPC great? It is not require any set how many cluster we want. It just find them naturally. It will find them with their density and distance. Now we will see that how we implemented this. Like there are 2 points. First, like in DPC, the core idea is like fall to the 2 points. First is a local density. Second is a higher distance to the higher density. For a higher density, for each earthquake, we count how many other earthquakes fall within a small cutoff distance. And these give us an idea of how crowd or important that location is in the data set. The second is a distance to higher density. Once we know that the densities, we find out how far each earthquake is from another one that has a higher density. The idea is that if an earthquake is a dense and far from anything denser, it's likely a good candidate for the cluster center. After that, we came to the how we implemented. The first, we tried the basic version using all the pairwise relations. But it was too slow, no doubt, it was very slow. But it was improved by switching pair radius neighbor graph using the Python skitlearn. This means we only stored edges where two earthquakes were within a cutoff distance. It is dramatically reduced memory and time both. Like it is reducing our time like 6 seconds to just 0.24 second. No doubt, sometime it fall between 0.30 to 0.40, but it's basically 0.24 second. Uh, Especially on a global earthquake dataset, which is fall under a 2.5 to 4.5 magnitude. Uh, Now this is we will call about we will say about the data and experiment setup. Like for our analysis, we used a real earthquake data set from the US covering a 1 month period from April 3rd to May 3, 2025. This data set includes 1,241 earthquake events with magnitude between 2.5 to 4.5. Like usually we standardize four features: latitude, longitude, depth, and magnitude. Because latitude and longitude for the distance and for the particular distance that where it is happening, depth for in how much distance, in how much depth was a center, and magnitude that what is the power of that. Before running that clustering, we tested a multiple algorithms like the original DPC and our optimized version DPCfast. Like like K means and DB scan. We evaluated this, but it's based on the Ceolithis code, which measures the cluster quality and runtime, which measured like efficiency of this. We also use the visualization like row delta graph and world map to check if cluster made tectonic sense or not. Here I'll say about the delta row, the decision graph. This figure show the decision graph, a core part of a DPC method. Here the each point represent the earthquake. You see the x axis row, how many neighbors are nearby. And in a y axis, you will see delta, the distance to the next denser point in the top right corner marked in a red are cluster center. They are both dense and far from any denser neighbor. So the denser blue region you see the down there, it's a near the x-axis include the ordinary earthquakes, which inherited the label from the closest red center. This is the nav DPC geographical cluster. Here we can see how DPC cluster earthquake on map. Like there are 5 distant cluster and each colored code like a orange, blue, green, red, and purple, which represent the different latitude, longitude around an earthquake patterns and the power of the measurement. Now the key point is that these clusters follow tectonic plate boundaries, especially in the Pacific and Nazca region. These show that DPC is like capable of bending and adjusting to the natural fault line curve. Something K means can't do. From this, my friend Ganesh will show you that how this graph and this works.
Hello, I am Ganesh. Now I'll explain DBScan result. In contrast, here's the result from DBScan with a fixed epsilon equal to 0.5. Notice how it breaks up continuous regions into many teeny groups and even marks many offshore events as noise, black dots. That's because one global epsilon value doesn't work well for areas that have both dense and sparse events. This highlights how sensitive DBScan is to parameter settings, especially for global earthquake clustering. Now, here's the optimized version, DBCfast. It gives the same five clusters as the original DPC, but much faster. The key difference is that it uses a sparse radius based graph to avoid computing every pairwise distance. As a result, it runs in real time and still keeps the core strength, like automatic cluster center detection. This makes DPC fast perfect for daily analysis in seismology. Now I will explain runtime benchmark. Here's the comparison of runtimes for all four methods. Like first one is k-means is the fastest. It will take 0.008 seconds. And the second one is DB scan. It is also fast, but it takes 0.019 seconds. And the third one is DBC fast takes just 0.24 seconds, but naive DPC takes 5.88 seconds. So while k-means is faster, DPC fast gives better clusters, especially when shape and density vary. This makes DPC fast a great balance between speed and accuracy. No method is perfect. There are some limitations here also. And DPC fast has a few limitations too. If too many points are close together, even the sparse graph can get larger and slow down. Choosing cluster centers from row and delta graph is still manual and may differ between users. Also, this version doesn't yet track time-based changes, so we cannot study how clusters evolve like aftershock sequences. Still, there are some problems that can be solved in future versions. Now, let's reflect on what we have learned. DPC fast keeps all the strengths of DPC, like finding clusters automatically and interpreting results using row and delta graphs. But instead of building a full distance matrix, it connects each point only to nearby neighbors. This means much less memory is used and it works much faster, like from 5.9 seconds down to 0.24 seconds for 30,000 exabytes. This making clustering scalable for big seismic data sets. So, in conclusion, even though it's faster, DPC fast is just as accurate as traditional methods. It works well on both synthetic datasets like Gaussian blobs and real world data. Compared to k-means, which assumes spherical clusters, and dbscan, which is sensitive to epsilon, DPC fast stand out as a balanced, efficient, and interpretable solution. It's especially powerful for clustering global earthquake patterns where both shape and density vary a lot. These are the references which we have used in this project.
Thank you, sir.